Okay, good. So we are now recording. It's 9:44 a.m. Pacific Daylight Saving Time, right? And very soon we are going to turn our clock back, right? Back now, forward. Spring forward, fall back. Let's see when is the date for that. Daylight savings. March 9. March 9 is going to be this Sunday, from Saturday to Sunday. Okay, so remember that? And what do you need to know? Go. And let's see where I stopped here. Okay, I provided you with the electric potential of a point charge. Okay, and I told you about the the equipotential surfaces. Why do I introduce you to equipotential surface? There's a reason why we introduce you to equipotential surfaces, okay? And that's something that you're going to continue doing in the lab that we are covering, okay? Why do we introduce the equipotential surfaces? Right? Surfaces. Okay. We do that because there is a very important relation between the equipotential surfaces and the electric field. There is a relationship between the equipotential surfaces and the electric field. Even better, there is a relation, not just between the equipotential surface, but not just the equipotential surface, but also the potential itself, the electric potential itself. Okay? So what do you have to know? I'm not going to prove that here for you, but you have to know that the relation is the following. The electric field is normal to the equipotential to a given equipotential surface. And we saw something like that here, right? So here we go, let's take a look. Right in here, we have equipotential surface. Do you see that? So this electric field right in here, this point is normal to the surface. So is this electric field right in here and this electric field right in here? The electric field is tangent to this electric field line, okay? So every point where the electric field crosses an equipotential surface, the electric field itself is going to be normal to this surface. Okay? That's what you have to know. Right in here is normal and so on. Okay? And again, normal means, I already told you what normal means, right? Normal means perpendicular to a plane tangent to the surface. Here you go. That's the one. And normal means perpendicular to a plane tangent to the equipotential surface. That's what you have to know. And there is a relationship between, mathematical relationship between the electric field and the electric potential mathematical relationship between the electric field and the electric potential. It's going to be like that. E equal to delta B over delta R. And there is a negative sign here as well that dictates the direction of the electric field. Okay? For the case of a uniform field, okay, the above relation becomes simpler. Instead of delta R, the delta R is replaced by the delta X. And we're going to see that in the lab that we are doing. Okay. Going back here to the book, here you go. Here you go, here's the electric field, right? There's a point charge. The equipotential surfaces for a point charge is a sphere, is a spherical shell. And the electric field is going to be normal to this spherical shell. There's a 90-degree angle. It's not 90-degree angle with the spherical shell, okay? It's a 90-degree angle with a plane tangent to the spherical shell. Plane tangent to the spherical shell. Here you go. That's the electric field lines again that you saw there in my notes. Notes here that we have a planar equipotential for this dipole charge distribution. Okay. At this point here, the electric potential is going to be exactly 0 because the electric potential due to this charge in this surface cancel out the electric potential due to this other charge. And at this point here, the electric field is going to be in the horizontal, 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 horizontal. All right? That's the only place where the electric field, the electric potential is 0, and the electric potential and the electric field in which the electric potential is 0 and the electric field is horizontal. That's the only place in this distribution here. Okay. Okay, here is another case, which is the first lab. It's the illustration pertinent to the first lab. 2 parallel, uniformly charged parallel plates. One is a positively charged, the other negatively charged. And the equipotential surfaces are parallel to those 2 parallel plates. And the electric field is going to be uniform, pointing from the left to the right in the horizontal direction. Okay. Okay, the electric field and potential are related. Okay, and the potential difference. Let's do this example. Okay, the plates of the capacitor, figure 19.15, this one that I showed to you, are separated by a distance delta S. This delta S is giving us a numerical value, 0.032. And the potential difference between them is, minus 64 volts. Between the two blue equipotential surfaces, there is a potential difference of 3 volts. Okay, two blues, okay. Between A and B. Between A and B. When we go from the positive plate to the negative plate, the electric potential decreases, okay? Now, minus 3 volts between B and A. Notice that the potential is decreasing, right? From the left to the right. VB minus VA. VB minus VA is minus 3 volts. What does it mean? It means, again, that the electric potential is decreasing from the right to the left. Find the spacing between the two blue surfaces. Okay? Think about that, how you're going to do that. You already have everything that you need. Don't look at the answer. Try to do that on your own. Let's see, example in the book. Example 9 in the book. Example 9 in the book. Chapter. Chapter 19. Chapter 19. Okay. Two parallel plates uniformly charged with positive and negative charges respectively. Okay. The distance between them is 0.032 meters. Is delta S. You put that delta S maximum, right? That's it. Delta S between the plates. Plates is 0.032 meters, which is 3.2 centimeters. Yeah, 3.2 centimeters. A little bit more than an inch. Little bit more than an inch. Let me get this thing here fixed. Symbol. Plates. Okay, what else do we need to know? The electric potential difference between them, between the negative plate and the positive plate. Okay, the electric potential between the negative plate B and the positive plate A is, let's write it down, electric potential difference, okay? Is, you got VB minus VA is equal to minus 64 volts. Minus 64 volts. Between the two, okay, uppercase B and uppercase A, right? The electric potential difference between two equipotential surfaces, lowercase b and lowercase a is closer to A, to capital A, okay? Is, let's see, what is the, is minus 3 volts. So B minus A minus 3 volts. Find the spacing between, not the spacing, find the distance, right? Distance, delta S. Distance, delta S between these two equipotential surfaces. That's what is asking. Okay. One very important point, use the fact that the E field is uniform between these two plates in the volume, right? Is uniform within the volume between these two plates. Okay, that's have you thought about that? You know how to solve that? Just go back to your definition of electric field. Okay, here you go. For a two parallel plates, okay, the electric field relation can be simplified as being that delta V over delta X with a minus sign. Okay. We already know that VB minus VA is equal to minus 64 volts. And we also have the spacing between the positive plate and the negative plate. Okay, delta X is going to be XB minus XA. So let's go to the next step here. Oh, no, just straightforward application of formulas, right? So here you go. That's going to be VB minus VA is minus 64 volts. XB minus XA, here you go, is going to be the delta X of the plates. It's going to be 0.032 meters. And then we gotta get minuses minus cancel, right? And all you have to do now is to do the math. 64 divided by 0.032. I'm getting 2,000. 2,000, and the unit is volt per meter. And by the way, and that's the value of the electric field. Volt per meter can also be written down as Newton per Coulomb. It's the same, exactly the same unit, written in a different way. Okay, I can prove that for you. just by doing dimensional analysis. Just by doing dimensional analysis. Because the electric field is uniform throughout that volume, okay? What you have right in here is going to be equal to this one as well. Lowercase b, lowercase a, lowercase b, lowercase a, right? And now you gotta use lowercase b minus lowercase a is minus 3 volts. And we want to know this guy here. I'm gonna put highlighted. That's what he's asking, right? Find the between the triple potentials, okay? He's calling delta F, but we can also call delta X. We can also call delta X. And I'm going to put that between A and B. Now let's put between B and A, just to show to you that B comes before A, okay? And erase that. You already know that this electric field is 2000 newtons per coulomb or 2000 volt per meter. Let's use volt per meter, right? And now you can solve this equation right here. We can do, let's do one more step here. One more step. The negative cancels out with the negative. And then I'm going to put delta X dA. Delta X dA. Like that. That's the equation that we have to use to finish our solution. Okay. Volt cancel out with volts. It becomes 1 over meter. And now you have to do is to solve for delta X dA. We're going to invert it. When we invert this one as well. And 2000 becomes 2000 to minus 1, right? Let's do the math. Delta X dA is going to be 3 times that. Three meters divided by 2000. Now I don't need the minus 1 anymore. B divided by 2000. I'm getting 1, 2, 3, 1 millimeter and a half. 1, 2, 3. 0.0015, 0.0015 meters, which is equal to 1.5 millimeters. Okay, let's see if that matches the book. Let's see, solution, reasoning. 1.5 millimeters, 1.5 times 10 to minus 3 meters. Okay. That's this case is easier, is the easiest of all they're going to see, okay? because the electric field is uniform. If the electric field is not uniform, then it's a little bit more difficult to solve the problem. In certain cases, you even need calculus. Okay, that's okay. So we are done with this, and we are going to do something similar like that in the. Okay, we will do something similar in the lab, in lab one. Lab one. In this first lab, we will calculate the electric field between two charged plates. Okay? Here we had to calculate the field, right? Here we also calculate the field, but he asked for something else in addition to the field. In order to solve for this problem, you had to calculate the electric field because you had to solve the distance between the two equipotential plates. Okay. That's a nice example. And now I want to start talking about, let's go back to our syllabus here. 10. Let's see. We're going to start talking about electric circuits. Actually, it's not electric circuits. We're going to start talking about, capacitance. Okay? Capacitance and capacitors. Electric potential, capacitance, and capacitors. Let's get here the first version of our syllabus. If we have time, we start electric circuits as well. Capacitance. Let's put E circuit. Okay, electric circuit. E for electric. Electric potential, capacitance, and electric circuit. Electric circuit is going to be chapter 20. Okay. Now, capacitors and capacitance. Capacitors and capacitance. What is a capacitor, right? No, I'm going to write that down for you. Capacitor is a device that's sold, is a type of electrical device, is a type of electrical device that is sold in the internet. If you have familiarity with electrical circuits and electronics, you know exactly what a capacitor is. In electronics, you will know exactly what a capacitor is. But remember, this is a very important device, by the way. This is I cannot emphasize how important it is, okay? It's a very important device that you must learn, okay? Your cell phone, just like mine, right in here, has a bunch of capacitors in its circuitry, a bunch, okay? And what you also, what else you have to know? Any electronic device has a bunch of capacitors. and other electrical components. Electrical electronic components. Electrical slash electronic components. And I'm going to tell you something else. In electronics, we have only 4 types of devices. Okay? With 4 types of basic devices. With these 4 types of devices, you can put together almost anything. Think about that. People narrow down, they managed to narrow down to only 4 devices that you can now end up, using almost everywhere, just like my screen here, my computer screen. The computer itself is made up of 4 devices only, and capacitors is just one of them. Okay, these 4 devices are, I'm gonna put here. Let's see here. I'm gonna put here you go, capacitor, and I'm gonna get the capacitor. A capacitor, B, a resistor. These are capacitors. Instead of A, just put capacitors. Here you go. Resistors. Inductors. And the last one, transistor. Have you ever heard of the transistor? 4 basic devices in electronics. We are concentrated on this one here for now. Later on, we're going to learn about the resistor and the inductor. We are not going to talk about transistor, okay? We will concentrate on the first one, and later on I will introduce you to resistors and inductors. Transistors are reserved for a more advanced course in electrical circuits. By the way, transistor is so important. Later, by the way, just to understand how important a transistor is, the scientists who invented the first transistor won the Nobel Prize in Physics. Okay? Let's take a look at the internet. Just for the sake of transistor, who invented? William Shockley, John Bardeen, and Walter Brattain. And here you go. Here how transistors look like. There are different types of transistors out there. You can buy those things. They're very inexpensive because they're mass manufactured. Okay, here you go. History of the transistor. It's a semiconductor device. Let's see, history, origin. The first patent on the field effect transistor principle was filed in Canada. This guy filed, but Lillingfield published no research articles about his devices, and his work was ignored by the industry. Okay, In 1934, German physicist Dr. Oscar Hale patented another field effect transistor. There is no direct evidence that these devices were built. But later work in the 90s showed that one of Lilienfeld's designs worked as described and gave substantial gain. Oh, legal papers. I don't know that from Bell Labs, okay? Legal papers from Bell Labs patent show that William Shockley and a co-worker, Gerald Pearson, had built operational versions from Lilienfeld's patent. We're talking about legal papers here, you know, and when they start talking about legal papers, what's happening here? There's a lawsuit going on, okay? So Lilienfeld, there is no device, but later they showed that Lilienfeld design, the guy that he patented, okay? He patented, but he didn't publish articles about his device. Look at the problem here, right? You go ahead, patent, and by the way, patents are far more valuable than any paper that you publish out there. And for some reason, the Nobel Prize Committee ignored the patents from Lilienfeld. Okay, for some reason, the Nobel Prize Committee, most likely, you know, Lilienfeld must have, if he were alive, you know, if Lilienfeld was alive, he would have sued the Nobel Prize Committee. Okay, for this reason that they are talking about legal papers, right? Legal paper from Bell Labs. And when you file a lawsuit, okay, you have to disclose everything. If there is no lawsuit, Bell Labs was not going to disclose those. What is said here. So William Shockley and a co-worker, right, had built operational versions from Lilienfeld's patent, though their final transistor design were based on different principles, okay? And the Bell Lab works on the transistor emerged from wartime efforts to produce extreme pure germanium crystal. And let's see when those guys, 1948. At Bell Labs in 1948. Bell Labs doesn't exist anymore, okay? Unfortunately. Actually, Bell Labs, to be more precise, Bell Labs were bought by Nokia. But they got all sorts of Nobel Prizes, Bell Labs. One of them is the transistor. And if I were Lilienfeld, I would have sued those guys, you know? I have my patent, you know? The problem is whether Lilienfeld had a patent in the States or in Sweden. That's the problem. If he didn't have a patent in the States or Sweden, he wouldn't have much to do against the Nobel Prize Committee or the Bell Labs laboratory. Okay, so let's see when they won the Nobel Prize. Nobel Prize, here you go, Nobel Prize in Physics, 1956. Okay. The patent from Lilienfeld is when? 1920s, right? 1925. Filed in Canada. So 1950 something. He was maybe in his 50s. Maybe in his 50s. Yeah, at least 50 years old, Lilienfeld. So keep that in mind. Let's go back here to what really matters, right? I always like to share that with my students. Those 4 basic devices. Capacitors are very simple devices. Capacitor, you have already been introduced to one type of capacitor. Okay, there are all sorts of capacitors. I didn't tell you to use a capacitor, but I have already introduced you to a capacitor. Let's take a look at here, capacitor. You're going to see, you know, commercially available capacitors that you can buy out there. Okay, so here you go. Several different types of capacitors, okay? This is a cylindrical capacitor, this is a cylindrical capacitor. This one is the parallel plate capacitor. Do you remember the parallel plate that we're talking about? One plate positively charged, another plate negatively charged, separated by a dielectric. Otherwise, the capacitor is going to become uncharged. So this one here is like a parallel plate. It's not a square plate, it's not a rectangular plate. It's a circular plate, but it's still a parallel plate. And here's another type of capacitor that's used in radios. We use capacitors to tune your radio station, your favorite radio station, and older radios use this type of capacitor. Do you see the knob here to adjust for the frequency of the radio station? That's how they built these capacitors. This is a capacitor that you can adjust the capacitance of the device. Here, those devices, they have fixed capacitance, okay? But this one is that has a variable capacitance. You can adjust the value of the capacitance. And they are very inexpensive. You can buy those things for 10 cents, depending on the capacitor, okay? It was invented in 1745. Okay, the guy that invented didn't get the Nobel Prize at that time because there was no Nobel Prize yet. Okay, the guy that came up with the Nobel Prize had not even been born. And we have the symbol of the capacitor. Okay, those three symbols. We are going to concentrate on this symbol right in here. Okay, there's a difference between those three capacitors, okay? There is the fixed capacitor, and then there is the polarized capacitor. We do have polarized capacitors out there. That's the symbol. But concentrate on this symbol here. Two parallel plates. That's what this symbol means. Two parallel plates, okay? And this one here is a parallel plate with an arrow. The arrow indicates that you can vary the capacitance of the capacitor, okay? Again, concentrate on the symbol here of the capacitor. I'm gonna copy that and paste in my notes, okay? Symbol of a capacitor with fixed capacitance. We're going to get into capacitance very soon. There are all sorts of capacitors out there. Check Wikipedia, for instance. Check Wikipedia or your favorite electronics store. There is one in Torrance. I hope that they is still open, okay? Torrance Electronics. There is another one that I used to go that is, what's the name of that place there? I'll remember. Check Wikipedia and your favorite electronics store. Okay, for instance, in Torrance, nearby the 101, okay. Nearby the UCLA, right? There's a medical center there. And the UCLA Medical Center, the Harbor, UCLA, that's in the UCLA Medical Center, Harbor, right? There is an electronics store called Torrance, an electronics store called Torrance Electronics. Let's see if they're still around. It has been a long time that I haven't been there. There are all sorts of capacitors out there. Check Wikipedia in your favorite electronics store. For instance, Lawrence Electronics. Let's take a look at that. Electronics. Carson, on Carson Street. Okay? Lawrence Electronics on Carson Street. It's just nearby the exit, 101 exit to Carson. 1545, okay? I used to buy some stuff in there. Last time I have been there has been a long time, maybe 3 or 4 years. And there is another one in Van Nuys. Now I remembered. There is another electronics store in Van Nuys. But nowadays we no longer, right? Van Nuys, how do I? Van Nuys. Wow. Oh man, esqueci. I forgot the name of how you spell the city. Let's see. Van Nuys. Van Nuys. Yeah, Van Nuys. Okay, here you go. Van Nuys. Van Nuys. But nowadays we just order those things from the internet, right? Nowadays we just order these devices from the internet, and there is a bunch of companies out there. Mauser, for instance, they sell those devices. Okay, Mauser, you can go here, Mauser Electronics, just one of them. They have this huge catalog of electrical and electronic components. You go. We have Mausers all over the world. Here you go. We have here in Brazil. We have Mauser here in Brazil. Here are some of the devices. Let's take a look at the capacitors. 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 Rick, here you go. Capacitor hardware, capacitor kits. Let's take a look. Capacitor kit here. Here you go. Yeah, see here, this one here. Click to expand. This is a very lousy image, unfortunately. Yeah, I want to get out of here. Yeah, you can see it. G product details. Yeah, it's unfortunate that they have such a lousy. Let's see this one here. Capacitor kits. These are not capacitors. Just something else that they use with capacitor. Let's see. Kits, we're talking about capacitor kits here. Let's see this one here. Yeah, this is a capacitor. Different from the other ones that you saw, right? Do you see the terminals here? One terminal and the other terminal here. Capacitors have two terminals. One is for the positive and the other is for the negative. Okay, accumulate positive charges and negative charges. I don't want, let's see if I can get ceramic disc capacitors. Right in here. Let's see. Capacitor hardware, ceramic capacitor. Let's try ceramic capacitor. See the number 640,000 ceramic capacitors. Here you go. All sorts of capacitors. That's the one I should have gone the first time. Okay, here you go. Over to Zoom. I want something different from that. Yeah, that's another type of capacitor that you see here. Let's see. And no questions so far. Let's talk about the real thing, right? That I need to introduce to you. So Capacitors are made from two pieces of a conductor material. Okay? Let me first symbol of a capacitor. Symbol of a capacitor of fixed. He put the fixed capacitor. You know, I prefer to say fixed capacitance. Okay? And let's see. It comes to the point where I need to introduce you. Here you go, a capacitor, a generic capacitor. Okay, it's just two pieces of metal. Here I came up with a drawing of a very generic piece of metal. Here I have one piece, and here I have the second piece. Okay, those two pieces of metal are already considered a capacitor. They're not charged, but they are already consist of a capacitor. The simplest capacitor you're going to see out there is the two parallel plate, planar parallel plate capacitor. Okay, just like we were doing in the lab. And here you go. They have a distance between them. Okay. And whenever you charge those two pieces of metal, you develop also a potential difference between them. That's why I have delta V here. Now you have a charged capacitor, a capacitor that can be used to do some useful work. Okay? Here you do have a capacitor, but this capacitor cannot do any useful work whatsoever because it is uncharged. Because this capacitor is uncharged. When you charge those two pieces of metal, now you can use them to do some useful type of work. Okay? Now, the parallel plate. Here you go. Parallel plate capacitor, just like the one that we are using in the lab, our first lab, right? One plate, the second plate right now is uncharged. When I connect those plates to a battery, the negative terminal of the battery, this plate becomes negatively charged. The positive terminal of the battery connect to the other plate, become positively charged. And now the parallel plate capacitor is charged, and you can use it to do some important useful work. Okay? And at this point in time, you already know that when you have those two plates charged, the electric field is going to be uniform with equipotential surfaces there in between. Okay? There's electric potential difference between them. That one type, the simplest type of capacitor. But we also have a spherical capacitor, spherical shell capacitor, right? One sphere concentric with another sphere, uncharged. And then you can charge those two spherical shells. One with a positive charge, the other with a negative charge. Okay? When we charge them, you have an electric field. And not only we have an electric field, but we also have energy stored in this capacitor. Which other one? We have the cylindrical capacitor. Okay? One cylinder concentric with another one. Cylindrical shell capacitor. Right now, again, this capacitor is uncharged, but I can charge it if we connected one cylinder to the positive of a battery and the other one to the negative of the battery. Okay? Here is the cylindrical shell capacitor seen from the top. Seen from the top. Okay. we do have an electrical field here on the inside between the shells, but no electrical field in the inside or outside. Electrical field is going to be 0. That's why I put E in is equal to 0. Cell as a capacitor. Oh, cells, okay. You folks that you are in biology, right? Many cells out there, they behave just like a capacitor. Many cells out there behave just like a capacitor, okay? We have the inside of the cell, and then we have the membrane. And I'm gonna make this membrane a little bit thicker. So let's see if this one works. Line. Nope, not this one. Compound side. With. Yeah, okay. See that? I'm making the membrane thicker and thicker, okay? So here we inside of the cell, we have an ionic solution. Let's say negative charges. And outside the cell, we have the environment where the cell is living, right? This thick line represents the membrane of the cell. Every time that we have this distribution of charges here, you're going to end up having an electric field here in the membrane. And the cell can use the energy in this electric field to do some work there inside, okay? It's amazing how nature came up with its own capacitor, its own electrical devices. It's amazing, okay? There are many, let's say devices, right? Invented by Mother Nature that behaves like a transistor, that behaves like a semiconductor device, that behaves like a capacitor, and so on. And we poor humans beings, Mother Nature invented that billions of years ago, right? We poor human beings invented that only just recently, in the last century, in the 20th century. Okay, so we have all sorts. Let's write it down. I'm made of two pieces of conducting material, conductor material. But there is more. These two conductors must be separated by a dielectric. Okay? To be considered a capacitor, those two pieces of conductors, they must be separated by a dielectric. They cannot be in electrical contact with each other, okay? So what can be a good dielectric? Air, for instance, is a good dielectric. If I have two metal plates, here you go, consider that two metal plates separated by each other by air, we can have a parallel plate capacitor here. Why do you mess? Here you go. Air, for instance, is a good dielectric, So is pure water. Pure water, wood, mica, glass, plastic, etc. Okay? So we have 3 elements only for a capacitor. 2 metal devices and 1 dielectric medium separating the 2 metals. Okay? Okay, keep that in mind. So you can have a very good picture of a capacitor. Okay, we do have a very nice type of capacitor, a macroscopic capacitor that's sold out there just for you folks to have an idea. Let me see if I can find it. Capacitor. Let's see if I can find it here. Capacitor for educational purposes, right? For educational. Here you go. Let's see if they have one here for education. It's not what I want. Let's see. Capacitor. Large capacitors. Large capacitors. Let's see if they have it here. Large. Not what I want either. Yeah, there's a very nice. We have a very nice capacitor there at the college that I like to show our students. Let's see if they, those capacitors that you see right in here, you cannot see on the inside of them, okay? All those devices that you see, you cannot see the inside of them. But that is, oh gosh. If I find, I'll let you know, okay? But let's move on. Let's move on, okay? Now that we define how a capacitor is built, let's define, now that we have defined how a capacitor is built, let us quantify. Let us learn, let us see how we can quantify a capacitor, right? We quantify a capacitor by its capacitance. Okay? There is a number associated with a capacitor, and the mathematical definition of capacitance is, is big C make sure you memorize this relation of K is going to be delta V over delta Q, okay? That's how we define the capacitance. So if we have, let's say, go back here, you're gonna charge the capacitor. Okay, let's get the parallel plate capacitor. Here you go, we have the parallel plate capacitor charged. We know, we are going to measure the potential difference between those two plates, which is delta V. You divide by the amount of charge that this capacitor carries, right? Holds, and you get the capacitance. Simple enough? Okay? Simple example. Let's take a look again at Wikipedia, right? Let's see. We have, they have a maximum voltage here. Okay, 35 volts. Okay? You cannot exceed 35 volts in this capacitor. And then they have another number here, 4,700 microfarad. Okay? What this number is all about? It's not charge. It's not a charge. Okay? This number that you see right in here is the capacitance of this capacitor. You can charge this capacitor anywhere between 0 volts and 35 volts. You exceed 35 volts, you're going to burn your capacitor. You won't be able to work with it. Okay? See the two leads here of the capacitor? One end is going to be positively charged, the other end is going to be negatively charged. Okay? That's the capacitor is fixed capacitance. So let's, so here you go. The unit of capacitance is, you have to know that, the unit of capacitance is the farad. The farad, represented by F. Okay? Capacitors, real life capacitors, we go. Real life capacitors can carry only so much voltage. Okay? If you exceed this voltage, you can damage your capacitor. So let's do a simple example. Simple example, right? We are going to do an example based on this capacitor that you see right in here. Simple example. A capacitor can hold, can be, let's say, can hold a maximum voltage of 35 volts. Very simple. Example. Its capacitance is known to be 4,700 microfarad. Symbol. Okay? Let's make sure it's 4,700. Yeah, 4,700. See? Microfarad. Okay? It doesn't tell you the maximum charge. Okay? It tells you the maximum voltage. Okay? What is the maximum charge that this capacitor can carry? Okay? Solution. Solution. Just use the formula of capacitance right in here. Okay. You want to know the value here, but don't forget, you want to use the maximum voltage, right? Oh, max. And you want to use to find out the maximum charge, right? It doesn't matter if you have the maximum voltage and the maximum charge. It can be any voltage and any charge. The capacitance will always be the same. Okay, that's the nice thing about capacitors. That's the nice thing about this capacitance. Okay, very important. No matter what voltage and charge you use, comma, the capacitance will always be the same, okay? Keep that in mind. It's a constant of the device. I'm going to write it down here. The capacitance is a constant of a given capacitor. No matter how much you charge, no matter how much the voltage you put between the plates, provided you stay within the maximum voltage, right? The capacitance will always be the same, okay? So here you go. the correct would be to put this thing right in here in the right side, right? So here you go. We know I'm gonna copy and paste right in here. We know delta V max. We know the capacitance. What we do not know is how much charge, what's the maximum amount of charge that that capacitor can carry. So I'm bold facing it for you. That's what we want to find, right? I'm going to copy it, this equation again and paste below. Delta Q is going to go to the left side. And the capacitance is going to go to the right side, right? And I'm going to replace those values with a numerical value, 35 volts. And this one here with the capacitance value, 4,710. Let's see, times 10 is microfaraday, right? So it's micro is 10 to minus 6. 10 to minus 6 farad. Okay, now you can do the math. You can do the math. Let's do that. 35 divided by 35 divided by 4,700. And then I have to multiply by a million. 2, 3, 1, 2, 3, right? 10 to minus 6 downstairs is 1 million upstairs. Make sense? And let's see what we get in terms of charge. That's a loss of charge for me. Let's see, there's something wrong here. Microfarad for oh yeah. Yeah, that's okay. That's what I'm getting. 7,446.81 coulombs. Okay. I can even put that, here goes, simplify. Here's 4.7 becomes 10 to minus 3, right? 10 to minus 3 goes upstairs. When it goes upstairs, it becomes 10 to the cube. Okay, and we get that number that you saw. Which is 7,446 coulombs. Volts divided by Faraday is coulombs, is loss of charge. That's the maximum amount of charge that your capacitor can carry. Okay. What time is that? 10:57. Any questions about that? We are going to move. I'm going to take attendance right now. So we can have our break. Roster. Notes, syllabus. Grade roster. Must be here. Okay, must be here. Nope. Here. Spring. Oh man, where's my roster? Let's search here. Nope. Am I in the wrong place here? Spring 25. Let's see. P07, P38. Yeah, okay. For some reason, didn't find the roster. Okay, open file location. Ah, okay, it's in P07. I'm gonna put it in the Spring folder. Yeah, here you go. Now it's in the place where I wanted. I'm hearing from a student that she's not accessing the calendar, right? If you haven't been able to access the calendar, let me know. I talked to another student that was here, and she told me that she can access. It was Elizabeth, right, Elizabeth? You're able to see the calendar there in Canvas. I'm talking about the calendar in Canvas, okay? So let me write that down here for you so you understand what I mean. Please let me know if you cannot visualize. Let me know if you cannot visualize the calendar in Canvas. Yeah, Elizabeth has been able to visualize it, right? Anybody else who has been able to visualize? And let's see, course. Make sure you go to the courses 11, right? 911 section. Where is the calendar? View calendar, right in here. As of now, we have just the lab one that's due next week. Okay, check if you can visualize this lab one that's due next week. Okay, Elizabeth can do that, but then there is another student who cannot do it. I want to hear from you all. Okay, please check Canvas. Let me know if you visualize it and write down there in the chat window. Okay, and then let's go here. Today is the 3rd. Abir Ahmad, are you there, Abir?
Yes, I'm here.
Okay, thank you. Nestor, are you there, Nestor?
Yeah, I'm here.
Okay, thank you. Next is going to be Monte. Let's see, Monte Ambachian. I don't see Monte here. Okay. Next is Hasti Amin.
Yes, I'm here.
Okay, thank you, Hasti. Isabella Ballesteros. Okay, Bianca can see, now you can see that, Bianca? That's good to know. Okay. Okay, so Isabella Ballesteros. I don't see Isabella here. Okay, that's Justus Bowden. Are you there, Justus? I see that I saw Justus logging in here. Okay, doesn't look like he's here. Next is Alexandra Burmistrova. Okay. I can see Alexandra here in my Zoom roster, but I cannot hear from Alexandra. I'm gonna put a star here. Benjamin Carvajal. Okay, yes, I can see the light. Oh, good. Thank you, Benjamin. One more, let's see. I'm gonna document here, right? Calendar. Yeah, when I call you, just go ahead and tell me if you can see the calendar or not. Bianca told me that she can, right, Bianca? Okay, yes. Elizabeth is Castellano. Elizabeth also saw it. Brianna Carrillo, can you see are you there, Brianna?
Yeah, I'm here and I can also see it as well.
You can? Good.
Yeah.
Okay, thank you. Elizabeth, are you there, Elizabeth? Yeah. Right. Next is Natalia Cordoba. I don't see Natalia. Yeah, I don't see Natalia here. Justus just joined us. Okay, Jacqueline Delgadillo.
I'm here.
Thank you. Do you see the calendar there, Jacqueline?
Yes, I do.
You do? Okay. Thank you. Next. Okay, so looks like whatever problem we had has been fixed, right? Jenny Diaz, are you there, Jenny? Yes. I don't see Jenny. Next is Valerie Diaz.
Here.
Thank you, Valerie. Next is Juan Scalera. Okay, thank you, Juan. Bianca?
I'm here.
Thank you, Bianca. Dana Gomez.
Yes, I can see it.
Okay, thank you. Edwin Gonzalez. Edwin.
Professor, I have a quick question for you.
Yeah, what's that?
I'm not Edwin, but I was having small like problems with like my computer and like my internet. It's gonna be like the name Justice. I just like want to make sure that that you have like the attendance down for me just in case.
Okay, Justice, right?
Yes,
Just-
sir.
Justice Bowden.
Yes, sir.
Okay, good. So, and now Edwin Gonzalez replied, right? Thank you, Edwin. And what about Alexandra? Alexandra, are you there?
I'm here.
Okay, thank you. And Ili Gonzalez.
I'm here and can see on the calendar.
Okay, thank you. I'm gonna put it here, yes. Manuel Hernandez.
I'm here, Professor, and I can see the calendar.
Good, thank you, thank you. And Samantha. Samantha Hubbard. I don't see Samantha here. Faiz Hussein. Faiz Hussein didn't show up, huh? Didn't ever show up. CJ. I got a message from CJ.
You hear me?
Okay, you're there. Okay, thank you. Next is Luis Leal. Looks like Luis Leal also is not coming, right? Amber Lopez. Are you there, Amber? I see you in my Zoom roster. I'm gonna put a star here for your attendance. Arely Lopez.
I'm here and I can see the calendar as well.
Oh, thank you. Genesis Lopez.
I'm here.
Thank you, Genesis. Next, Mary Michaelian.
I'm here.
Thank you. Ramon Olivares.
Here.
Thank you. Taylor Forn. Taylor. Yeah, doesn't look like Taylor is here. Jeremy Pittman. Are you there, Jeremy? That doesn't look like Jeremy is here. Stephanie Ramos. Stephanie with S, right? Okay, I can see Stephanie here. I cannot hear from you, Stephanie. I'm going to put a star next to your name. Leslie Rios.
I'm here.
Thank you. Jason Street.
I'm here.
Okay, thank you.
And yeah, I see the calendar.
Okay, oh, thank you. Emma Torres Navarro.
I'm here, and I can
Thank
also
you.
see the calendar.
Okay, thank you. Cindy. I don't see Cindy. Cindy never showed up, right? And then we have Nuhamin, never showed up either, right? Nuhamin, let's see. Nuhamin won't be moved. Nope. Okay, so only 2 students that haven't replied to my call. Let's give another opportunity for them. Stephanie Ramos, are you there? And Amber Lopez. 24 here. 20, okay, 26. Let's go for our break. It is break from 11:10 to 11:25 a.m. Okay? And I see you in 15 minutes. See you. Bye-bye. I'm back here. Okay, so here we go. Now what we're going to do, we're going to calculate the capacitance of parallel plate capacitor in terms, we're going to obtain, okay? Obtain capacitance of parallel capacitor in terms of genetic variables, okay? Parallel plate capacitor. Okay, just recall that the electric field of a parallel plate capacitor, is given by, you remember that? It's always good to have those memorized. If you don't have memorized, at least you must have, a little piece of paper there next to you to tell you with those important formulas, okay? The sigma, okay? And then, do you remember that? Epsilon. No, epsilon. Is that the one? No, that's not the one. Let's see. I'm just gonna copy and paste from elsewhere. Epsilon. Here, epsilon naught. Do you remember that equation? Two parallel plates, right? We parallel. I made a derivation of that, right? Let's see if I can find it. Yeah, we're getting there. Let's see. No, it's not here. Let's see. I'm trying to find when I made the derivation of the electric field here in class with you. Let's see. Go more. No. What a shame. I can't find it. First step, recognize the area vector. Let's see. Example 2 next to spherical shell. Okay, here. And by the way, the book derives that in a different way than I did, okay? I don't like that way that they do. This is not the only book who did that derivation. I think it's flawed. The derivation of the electric field of a parallel plate capacitor, right in here. Okay? Yeah, here you go. Right in here. I think the way I derived using Gauss's law is a better way. And I have seen, more than one book doing the same derivation that your book did, which again, I think is a flawed way of deriving the electric field. They get the right answer, but the procedure, I don't agree with the procedure, okay? Let's see. Okay, Amber is here. Let's see. Amber Lopez. Yeah, thank you, Amber. And what about Stephanie? Are you there, Stephanie? Stephanie must be away from her computer. Okay. One more student, two students trying to come in. Okay. Lee Gonzalez. So here you go. That's the electric field of a parallel plate capacitor. And I'm going to here write sigma is the charge density, surface charge density, which is equal to the net charge divided by the area of the capacitor. Okay. That's what sigma is all about. Okay. And let's not forget the definition of capacitance is this one. Now we are going to do a derivation, but we are going to do derivation in terms of the symbols, not the numeric derivation, but a symbolic derivation, okay? That's what we have here. On the top of that, what else do we know? We do know that there is a relationship between the electric field and the electric potential difference, which is this one right in here, okay? That's the relationship between the electric field. And by the way, the capacitance is always a positive number, okay? So when I put delta V here, I'm actually, delta V over delta Q here, I'm actually state the more precise definition of capacitance is this one right in here. It's always positive, okay? Now, there is a relationship between the electric potential and the electric field, which is this one right here. For a uniform electric field, we can here write for a uniform electric field, comma, we can here write the above equation as delta V equal to E delta X, okay? To E delta X. I'm gonna put my delta V here, and there is a negative sign in there, okay? So making our, X naught, this delta X would be X minus X naught. Making my X naught equal to 0, put my X naught at the origin of my coordinate system, then we end up with a relationship for the delta V and the electric field as being that. Assuming, okay? Placing the origin of our coordinate system at X naught, the above equation reduces to, and I'm gonna here write that, okay? Just bear with me here. You go, can be reduces to, and then I erase this one like that, okay? Reduce to. So what does it mean? It means, here you go. It means that from left to the right, you know, the delta V changes linearly with X. Suppose I put an X axis in this direction here, okay? So that's what it means, okay? Linearly. So now what would be, suppose the distance between the plates of your capacitor is D, okay? Let's take a look again. The distance between those two plates is D of delta. Okay? Consequently, the potential difference between the plates will be given by, okay, E times D. Okay, and I'm going to here write that also. You go Q over A epsilon naught, right? Q over A, oh, Q over A epsilon naught times D. Make sense? Oh, don't forget the negative sign, right? Don't forget the negative sign. Now we are ready to determine an equation for the capacitance of any parallel plate capacitor. Okay, so here you go. We get this one right in here. Place right in here. We already have our delta V. Our delta V is this equation right in here. Delta V here means the difference, the potential difference between the two plates, okay? And here shouldn't be delta Q. Here actually should be Q, okay? Should be Q. And look what happens. Something interesting happens. This Q that, I'm gonna put the A epsilon naught downstairs first. Okay. And look what happens to the Q. It cancels out. It always happens like that when you're calculating capacitance, okay? The negative sign is going to disappear because we are taking just the magnitude of the resulting equation. Q is going to cancel. D is the distance between the plates, is a positive number. Area is a positive number. Epsilon naught is a positive number. And look what we get. We get that the capacitance of a parallel plate capacitor depends on the distance between the plates and on the area of the capacitor. Okay, plus this constant here, epsilon naught. Let's see if I got, oh yeah, let's see. Oh, I'm sorry, let me see. I did it incorrectly. Let's see here. Yeah, it's not delta V over delta Q, okay? Let's go back to the book, double check. Is the inverse, let's see here. I want to double check with the book. Capacitance. Yeah, it's Q over V, okay? I was doing the, Q over delta V. And we have to correct everything else there. Let's see if you have, yeah, here you go. Q over delta V. Oh, that's why I got such a large number, okay? Here you go, should be Q over delta V. Okay, Q max over delta V max. Here, the same thing here. 16 is. Okay, is the inverse, is the Q upstairs. And now we have to undo this calculation, right? This one is supposed to be, 1 over C, here you go. It's easier for me to do 1 over C than to fix the other one. And then this thing's supposed to be -1 here. And then you do the math to figure out what's going to be the charge. Okay. Here, all of that should be raised to the -1. Fix. Okay. -1. -1, right? And then we end up with something like that. Gotta do this math here, okay? So Q over delta V. Now let's fix what we're doing here. Q delta V. Okay, this one is correct. What's not correct is this one here. Q over delta V. Okay, and this delta V goes downstairs. And Q goes upstairs, okay? And now A, okay, the Q cancels out with the Q, 1 and 1. The negative sign disappeared because we're doing the modulus here. The A epsilon naught goes upstairs. Okay, and that's the correct result for the capacitance of a parallel plate capacitor. The larger the area, the larger the capacitance. The smaller the separation between the parallel plates, the larger the capacitance. Note C. Remember, this is for the parallel plate only. Okay. Note C that the capacitance is a function only of the geometrical parameters of the capacitor, A and D, okay? Epsilon naught is just a constant. And by the way, this apply to the other capacitors as well. Okay? Whether it is a cylindrical, spherical, or any other geometric configuration of the capacitor. Remember that I told you that for this reason, it does not matter. Does not matter what is the potential difference between the plates of a capacitor. Okay? Its capacitance will always be the same. Okay? Whether you have 1 volt between a plate, the parallel plates of a capacitor, 2 volts between the parallel plates of the capacitor, 3 volts, and so on, the capacitance will always be the same. Okay? Notice that the capacitance. We can now also find the capacitance with spherical capacitor. We can also find the capacitance. The spherical capacitor consisting of 2 concentric spheres of radius A and B. Concentric spheres, okay? That's the key here. Concentric spheres. So going back right here to my spherical shell capacitor. Here you go. I didn't put the, one is A, the other one is B. A radius, B radius. What's going to be the capacitance, the formula for the capacitance, okay? What is the formula of this capacitor? What's the formula for the capacitance? For the capacitance of this capacitor, okay? Solution. Let's go ahead and copy and paste what we have here, right? Here you go. Now we have to calculate what's going to be the delta V of this configuration. Okay, recall that for a spherical charged shell, the electric potential inside it is zero. But the electric potential outside it is given by the potential of a point charge, right? A point charge is just a very small sphere, right? Do you agree with me? So here you go. The electric potential of a point charge is going to be given by B, KQ over R, right? KQ over R. For the inner capacitor, for the inner shell, I'm going to put V sub A, right? It's going to be KQ over R as well. And also, for the other one also, it's going to be the same. Okay, so here you go. Let me make an illustration here. Right at the surface, right at this inner surface, the electric potential is going to be, let's see here. And I'm going to do more than that. Here you go. I'm going to do something else. Here you go. I'm going to tell you that this guy here is A. Okay. I don't need the electric field here. I'm going to take away the electric field. Here's the radius A. I don't need the electric field here. And this other one is going to be the radius B. Write that. Okay. The electric field here inside is zero. The electric field here outside is zero. That comes from Gauss's law, right? If you put the Gaussian surface right here, there's no charge here inside. So I'm gonna, E right in here is gonna be zero. And outside is gonna be zero as well. Maybe out zero as well. So we have only an electric field here between those two surfaces, because this spherical shell, the electric potential of this spherical shell behaves just like that of a point charge. What does it mean? It means that between this point and this point, the electric potential is going to be given by this equation. I'm not even going to put sub A, okay? Electric potential is going to be something like that. Okay. Here, I'm emphasizing that's only between those two surfaces. Okay? At this very surface, the electric potential at A, and now I'm going to use the electric potential at A. I'm going to put like the electric potential at A is going to be KQ over A. Okay? KQ over A. And right in here on the outside, the electric potential at this other shell, at B, right, is going to be KQ over B. You get it? In between is going to be KQ over R. Remember that we want to get in order to find the capacitance, we must get the capacitance between the electric potential difference between this surface and this other surface, the difference, right? Between those two. So let's go back to our definition. Okay, here we go. Capacitance is, I'm going to put it VB minus VA minus VA. KQ over B KQ over A. Like that. Copy and paste. This Q here cancels the other Q upstairs. Right? And then we are left with K. The K can be taken out from the parentheses. 1 over K. From the, not parentheses, but the magnitude here. Okay. This number here is greater than this number. Consequently, when we take the magnitude, we can invert it as being 1 over A minus 1 over B. Okay, and we're getting there. I can go ahead and put them under the same denominator. Like that. Decay, we can put that in terms of 4 pi epsilon naught, okay? We can write that in terms of 4 pi epsilon naught. Let's do that. We go 4 pi epsilon naught. 1 over k is equal to 4 pi epsilon naught. And now we have the same denominator downstairs, b minus a. We place AB at the top, and just like before, we get that the capacitance of a capacitor is given only by its geometrical parameters. We found that out for the parallel plate capacitor, and we found that for the spherical shell capacitor as well. I'm gonna get this 4 pi k right here at the top to save space. 4 pi k right here at the top as well, okay? And now I got everything. And just to save space, let me see. I want to emphasize, let's see, I can put it outside just to emphasize. Okay, here you go. This term here is a function only of the geometrical parameters of the capacitor. There you go. 4 pi epsilon naught AB over B minus A. Okay. Let's see, there's another mistake here, right, in terms of the units. Let's see if I got it inverted. Not this one. Farad. Q over delta V. Yeah, I didn't say anything about. Okay, and by the way, let me just remember side, let's put an aside here, the unit of capacitance, square bracket is equal to the square bracket of, right, like that, charge over electric potential. Okay, here we go. It's gonna be Coulomb over voltage, and this unit shows up so frequently in physics that we call it the Farad, unit of Farad. Let's see what we did that here in the book. Dielectric constant. Let's see here. Constant, yeah. Q over VC. The dielectric constant. Okay, there's one more thing here that we have to worry about. I didn't cover it yet. We are going to cover right now. 12 o'clock, 11:40. Our break was is an application, right? We're gonna. Okay, let's do this one here. parallel plate capacitor filled with a dielectric. Okay. When we got this equation here, okay, and this other equation, I didn't tell you that, but okay, the previous two equations, for the capacitance, parallel plate, and spherical capacitor, comma, assumed that the medium, the dielectric medium between the conductors was the air / vacuum, right? Very important. That's why we ended up with the epsilon naught at the top, with the epsilon naught at the top of the equation, okay? Epsilon naught, this value is almost the same for the air and vacuum, almost the same. There is a slightly difference, okay? However, when we fill the volume in between the capacitor, the plates, right? The plates of the capacitor, between the conductors, okay? The conductors of the capacitor with a different dielectric material, we get a slightly different result, okay? Let's get it, that's a slightly different result. And that's what he's doing right here. That's what he's doing right here. Okay? So the explanation is a very straightforward explanation. Let me see if I have my own. Oh yeah, here, right here. Vacuum between the plates of the capacitor. Okay, when you have the vacuum between the plates of the capacitance is going to be that result that you got, this one right here. However, when you fill that with something else, like a piece of cardboard, you know, vacuum / air, let's put that / air between the plates of a capacitor. / air between the plates of a capacitor. Now, when you put something else there inside, like a piece of cardboard, a piece of glass, a piece of plastic, something else happens that changes the equation slightly, okay? And what's that? Okay, so this electric field that you see right in here, you know, is going to try to polarize this substance in between the plates. Okay, so that's because of the electric field. Okay, the electric field is going to try to rip apart the molecules of this material, and by ripping apart, I mean it's going to polarize the molecules that are inside this dielectric material. Can you picture that? The negative charges of the molecules of this dielectric is going to be attracted towards the positive plate of the capacitor. And the positive charges of the molecules of your dielectric material is going to be attracted towards the negative plate. Okay? With no electric field, you don't have something like that. With no electric field, the negative charges and the positive charge are going to be almost at the same place, okay? But then with an electric field, we are going to, I can even, come up with another, here you go. An uncharged, I want an uncharged, I'm going to illustrate that for an uncharged capacitor. And then I have to erase that, okay? I put this piece of cardboard there. The capacitor is not for uncharged capacitor. Here you go. The molecules are not going to be polarized. The molecules are going to be just as rounded, The negative and positive charges are going to be very close to each other. Do you get the picture? You have a situation like that when there is no electric field whatsoever. But when you charge your capacitor, there will be an electric field between the plates, and those molecules are going to be polarized. Okay? Okay, that's the situation of the molecules of your dielectric. They're going to be round. The positive is going to be almost the same, collocated with the negative charges. But again, once you charge it, the molecules are going to become polarized like that. There's one more thing, okay? Note, see that the electric fields go from the positive to the negative charges, right? Positive charges are sources of electric field. Negative charges are sinks of electric field. You get the same thing for those polarized molecules, by the way. Yeah. If you have this electric field of the capacitor going from the right to the left, you are going to end up getting another electric field from the left to the right, but inside the molecule. Inside each of the molecules. This is a very good model, by the way. Seems like I'm hand waving, but that's not what is happening. Now, color. Let me make it, here you go, like that. That's terrible. That's terrible. Let's get another color here. Red, brown, no, green. I don't like green. What about blue? Blue is better, right? Light blue. Here you go. Here's the electric field inside the molecules because of the polarization of the charges of the molecules, of the polarization of the molecules. Notice that the main electric field points to the left. The inner electric field of the molecules is going to point to the right. What does it mean? It means that we are going to have a net electric field that's going to be weaker. Did you see that? I'm drawing it as electric field lines, right? I have 1, 2, 3, 4, 5, 6 lines here because this electric field inside the molecules is pointing contrary to the outside electric field. The net electric field is going to be weaker, okay? Just like that. That's the story that I have to tell you, okay? So let's put that in the notes. And that's exactly what's written here too, okay, in the book. So now, something else happens, okay? However, when we fill the volume in between the conductors of the capacitor with a different dielectric material, we get a slightly different result, okay? The step-by-step is the following. The main electric field of the capacitor will polarize the molecules of your dielectric material. Okay, one. This polarization of the molecules result in an internal electric field produced by the polarized molecules. Okay. The electric field of the polarized molecules will the electric has a direction that is contrary to the main electric field of the capacitor. Okay, here you go. Consequently, the net electric field will be smaller than the original main field with vacuum between the plates. Okay. So how do you express that mathematically? Okay. Express that mathematically in the following way. The electric field with the dielectric inside is going to be the electric field with vacuum inside divided by a number kappa. That, by the way, is going to be greater than 1. Okay, so the situation is like that, right? The net electric field will be smaller. We say that, E is smaller than E naught. Okay, where E naught represents the electric field with vacuum between the plates. Between, not the plates, but let's put between the conductors is better. Conductors is a more generic name for the plates, right? Okay. Okay, recall that, E naught is equal to V naught divided by D, right? Recall that. If you have that for E naught, for E, we are also going to have something similar. E is going to be V over D, okay? But your nu E, I'm going to do like the following. Your nu E, I'm going to do like that. Your mu E is going to be given by E naught over kappa, which is less than E naught. Also, we have V we have something like that as well. Okay, I didn't change anything, right? I just put the V outside here and put the number 1 there. So you can have a better picture okay, of what we're doing. We can erase that. And then what else can we do? What else can we do? Okay, now I'm going to replace this E naught with this term right here. And you want to see what's going to happen. And okay, here you go. And here too, we have the same thing. Okay? Okay. And what else do we have? Okay, I'm gonna write that down here. E. Okay. Going back to what we had here before. V over D. Right? Now we have this equality. This equality. Oh, wait a minute. This equality here is supposed to be V. Okay, let's instead of doing what I did before, let's keep it V over D. All I'm doing here is replacing E naught with V naught divided by D, okay? Next step. What's going to be the next step? Next step, the D goes downstairs. V naught remains upstairs. What else? D cancels out with, oh, I'm not going to do that now. I'm going to do that in the next step. D cancels out with D. And then look what we get. We get that my V is going to be my new V is going to be V naught divided by kappa. Okay? So not only the electric field decreases by a factor kappa, the electric potential also decreases. Okay, conclusion. Not only, let's see, conclusion. Conclusions. I'm gonna put like that. One, E field decreases when we add a dielectric material other than vacuum. Electric potential also decreases. Okay? So I don't want that here. I don't need that. Let's do that again. Here you go. We got that. We got that from, a qualitative analysis, okay? Following this qualitative analysis, we notice that the E field must decrease, okay? Then the question is, what happens to the electric potential, right? Potential. What happens to the electric potential? Okay, recall that E naught is V naught over D. If E naught is equal to V naught over D, E is also V over D. Okay? But E is E naught over K. And we still keep a V equal divide, we still keep the same thing on the right side, just in a slightly different format. And then what do we do next? We replace V naught over D right in here. Okay, V naught over D. And now we start to get a relation between this V and the V naught. Okay? rearranging our equation, put the d downstairs, this d cancel out this d, and we finally get that the v is going to be less than v naught as well. Okay. So what time is that? 12:20. That's the conclusion that we get. There are other conclusions that we can draw from that too, but let's have our break first. It's 12:20 right now. 12:20 p.m. to 12:35 p.m. You know what? Our class ends at 12:50, right? Oh yeah, let's have a break. Otherwise, we're gonna get burned out. Okay? Even I am getting burned out too. So I see you in 15 minutes. 35, and then we do more 15 minutes of lecture. Okay? So I see you in 15 minutes. Okay, I'm back here. Start sharing my screen here. 3, okay, good. Okay, so what about, okay, we found out that electric field decreases, the electric potential also decreases. But what about the capacitance, right? What happens to the capacitance? Okay, so here you go. Capacitance goes like that. First, we calculate the capacitance without the dielectric, it's the C naught. Then we calculate the capacitance with the dielectric. The charge shouldn't modify. The charge should remain the same. Okay, the dielectric does not affect the charges because your capacitor is connected to a battery. And you have that metal plate of the capacitor, right? I kept Q here as being the same as this Q here. Okay? But notice that I made C naught here, I made C here, and V naught here, and V here. The Q remains the same, whether you have a dielectric or not. Okay, and now we are going to use that result that we got for the V. V is going to be V naught divided by that constant kappa. This kappa depends on the dielectric material. Okay, and I didn't mention that, right? No, and I'm gonna okay, kappa here. The constant kappa depends on the properties of the dielectric material. Dielectric. See here. And there is just a list of values for the dielectric material. For different dielectric materials for kappa, okay? It has no units. Let's see here. Okay, right in here. The book has vacuum and air. They are almost the same. Do you see that? The dielectric constant of the air is just an almost nothing here compared to the vacuum. That's why I keep on saying that the kappa for the vacuum and the air are almost the same. We are talking about less than a hundredth of a percent, less than a tenth of a percent. We're talking about less than a tenth of a percent. Here would be 1%. Here would be a tenth of a percent, would be 500ths of a percent. The difference is very small. But then, depending on the material, the dielectric material, for instance, Teflon is a dielectric material. Teflon is what is used in your frying pan, so stuff doesn't get stuck there at the bottom of the frying pan, okay? We have a layer of Teflon there. Benzene, 2.2. Paper, 3.3. Mica, okay, we know mica is a dielectric material that's found in nature, okay? Neoprene rubber, 6.7. Methyl alcohol, the liquid. Water. Look, water is 80.4 for the dielectric constant. It has no unit, this kappa. And let's we are calculating here what's going to be the capacitance, right? What happens to the capacitance when we insert a dielectric material? Here you go. This kappa goes upstairs. I'm going to put this kappa outside here. V naught. And look what we get. Q over V naught is C naught, right? And then look what happens. Although the voltage and the electric field decreases, the capacitance increases. A capacitor, the field decreases. There you go. When we add a dielectric material between a capacitor, within the conductors of a capacitor, the following happens. It's the electric field. The following happens. The electric field of the capacitor decreases, between the conductors of a capacitor. I'm going to put here other than vacuum or air. Decreases its electric potential. Also decreases 3, but its capacitance increases. Okay. Capacitance increases. What else can we do here? Well, we can also find out the amount of energy. Okay, what about the amount of energy, right? What about the amount of energy that the capacitor carries? Okay. First, we will get the, when I mean the amount of energy, I mean the amount of potential energy, okay? Potential energy. First, we get the potential energy of a capacitor with vacuum between the plates, okay? And the way we do is like that, first, we go for the definition of electric potential. Do you remember the definition of electric potential? The definition of electric potential is electric potential energy divided by the charge. Okay? And I can rewrite the electric potential as being the charge times electric potential energy as being the charge times the electric potential. We are recording, right? But then we are going to rewrite it in a slightly different way. We're going to rewrite that in a slightly different way. We are going to replace the delta V in this equation with the other parameters. I'm going to rewrite this delta V that you have right here in terms of Q and C. Okay, don't forget this is the definition of capacitance, right? So substituting the electric potential difference in the formula for the electric potential, we get the following. Okay, here you go. One more. Here you go. And we don't need the magnitude of the Q anymore, okay? Oops, not here. Like that. And look what we get. We get an equation that goes with the Q square divided by the C. Okay. Now there is a warning here. This is not quite correct. This is not quite the correct result. Okay, folks? The actual correct result is slightly different than the above, slightly different than the above, okay? I'm gonna put that in. Correct result is, okay? Yeah, it is directly proportional to Q squared. Yes, it is. It is inversely proportional to C. Yes, it's also inversely proportional to C. But then what's missing here is the half parameter, okay? Here is just a qualitative way of you remembering the relationship, okay? Q squared over C. Okay? There's a half. And we can rewrite this equation in two other different ways. We can rewrite this equation in two other different ways. One way, we replace the C with this equation that you see right in here. Okay, and I'm gonna put it Q over delta V. Okay? One Q cancels out with the other Q. And the delta V goes upstairs. Half Q delta V. There is one more way of rewriting this equation, okay? Going back to this one. three different ways of rewriting this equation. Delta V goes to the left side, right? Q stays right in here, like that. And now substituting it. Q goes right in here. Delta V. You go, right? And look what we get. I like this formula better. This last one, I like it better because it's easier to memorize. Okay, C delta V squared, all right? That's very similar to the equation for the kinetic energy, right? Half mv squared. Oh, it's 1250 already, right? So let me boldface the equations, three different equations. It's exactly for the energy of a capacitor, okay? And let's stop right now. And later on, next time when we meet, I'm going to show you what happens whenever we add the dielectric. What happens to the energy when we add the dielectric to the plates, okay? Any questions about that? So we will meet tomorrow, no, the day after tomorrow, Wednesday. And I'll see you in 2 days.
See you in 2 days. Thank you, Professor.
Bye-bye.
Bye, Professor.
See you, bye-bye, thank you.
Thank you, Professor.
Welcome.
Thanks, Professor. Have a good one. Take care.
You too.
Hello.
Yes.
Hi.
Hi.
I just wanted to let you know that I wouldn't be able to take the midterm on March 12th because I have a doctor's appointment in the morning.
March 12th.
And I was wondering if you needed a doctor's note for that.
Well, you're asking, okay. Well, we can postpone it. Let's see how is the schedule, how does it go. I think we can do that. I don't want you to miss the exam. Yeah, we can change, the date. Next time, remind me to tell the other student, okay? Can you take the exam on the 19th? Hello?
Let me see.
Can you do
Yeah,
that?
I can on the 19th.
Okay. The answer is
Okay, well,
yes.
okay. Thank you very much.
Okay.
Have a good day.
You too. Bye-bye. Hello, CJ. Do you need anything?